Hey everyone, this is homework for your mid-unit assessment day. Today we're going to be starting to get into domain and range in the upcoming lessons. So this is a review of your inputs and outputs. So for each pair of variables, you want to figure out what makes the most sense as the input and to try and use units with that. So as an example, if we're talking about the height of plant as a function of time, the input is time measured in days. Seconds would be too short of a period. Hours would probably be too short of a time period. So the number of popcorn kernels left unpopped as a function of time. So the input is time in seconds. And I'm going to say seconds because it takes, approximately a minute or so or maybe 2 minutes, to cook popcorn. And so how much is left would be best measured in seconds because it's a pretty small and short amount of time. The cost of crab legs is a function of the weight of crab legs. So in this case, the input is weight. And usually we measure crabs in pounds. You could potentially do ounces if they are small crab legs. All right, so for these, you have the input here because you know that the X value is your input. And so that is your input right there. For E and F, it's giving you the information. You just need to tell me what the input is, and it's pretty easy to identify, so those I'm going to have you do on your own. For number 2, it says write the equation or draw the graph of a function relating to variables. In this case, the input is the side length of a square, and the output is the perimeter. Remember, perimeter is adding up all of the sides, so perimeter of x would be 4x. This one is easily represented with an equation. The input in the time spent walking and the output the distance. In this case, because we don't have exact information about how long they're walking or how far they're walking, I would say that time in minutes is going to go here, distance is here, and ultimately over time, right, it's going to increase that distance. Here our input is time spent working out, time in minutes, and then our heart rate. And your heart rate is it's never going to start down here, right? It's going to start up here, and it's going to fluctuate. And maybe if you're working out more and more, your heart rate might start to go up a little bit, but it's just going to vary and waver across the board. Again, nothing specific here, but just showing that your heart rate may not be steady every time, depending on how fast or how much you're working out. All right, so the function W gives the number of ounces of water max drinks as a function of time in hours. Determine W of 2 equals 10. So remember, this is the input in parentheses, is the input, and that's almost always time in hours. So 2 hours of working equals 10 ounces of water that he drank. Use function notation to show that Max has had the same ounces of water at 180 minutes as at 45 minutes. Now notice we're doing time in hours, so I need to convert that to hours. So that would be W of 180 minutes is 3 hours, and then 45 minutes out of an hour is 3/4, so W of 0.75 or 3/4 of an hour. That would be the same amount of water at those 2 times. So if he's drank water and then he just stopped drinking water, then they would be the same. If Max has had 4 ounces to drink in 30 minutes, how would you write that in function notation? So W of 1/2 or 0.5, you can write it that way as well, is 4 ounces. So we can say W of 0.5 equals 4 as well because we're measuring hours and 30 minutes is half an hour. If Max has a water bottle that is full of water and holds 32 ounces and he drinks a constant 4 ounces per hour, show a function notation of how much water is left. So if we have water of function of time equals starting amount of 32 ounces, he's drinking it, and so we're looking at how much water is left minus 4 times the amount of time that he is exercising will tell us how much water is left in the water bottle. All right. This is function notation, right? This is not multiplication. This is saying the function of water is a function, the amount of water is a function of time here. What is the average rate of change from 1950 to 1970? So this is a practice with average rate of change. When you see this, you automatically should know you're creating a ratio here of something to time. In this case, it's population in billions to time. So 1970 minus 1950, that's our input of time. And then we're looking at the population of 1950, which is here, to 1970, which is here. Remember, our later value is first, so 3.65 minus 2.56. And so then you would go ahead and calculate that. You know that 1970 minus 1950 is 20 years. And then you are going to do 3.65 minus 2.56, which gives you 1.09 divided by 20 is going to be 0.0545 billion, right? So that's the population in billions growing per year, right? That is our unit rate. So again, your time, your input goes into the bottom, the difference, the later value minus the earlier value, and then in the outputs at the top, the later value minus the earlier value. In this case, it's population. All right, this last one is a park practice item, practicing writing functions, where we have a group of students who are baking 100 cookies. The students want to ensure that the price of each cookie offsets the cost of the ingredients. If the cookies are sold for 10 cents each, the net result will be a loss of $4. If all the cookies are sold for 50 cents each, the students will make a $36 profit. First, write the linear function p of x that represents the net profit from selling all the cookies, where x is the price of each cookie. Then determine how much profit the students will make if they sell the cookies for 60 cents each. All right, so if we are looking at a 50 cent each cost for 100 cookies, and the students will make a $36 profit. So we're writing the net profit from selling all the cookies, where x is the price of each cookie. So we don't know necessarily what the cost is that we're going to sell them for. So we're going to sell 100 cookies times x, and then we also want to offset the cost that will be for the cookies. So what is unique about this is we need to figure out how much we are spending to make the cookies. So if we sell 100 cookies at 10 cents each, that's how much we would make. And then we have to subtract the cost of making the cookies, which we don't know what that is. But we know that if we do that, we'll have a net loss of $4. So we'll be negative $4 in the hole. So that'll tell me how much this is if I solve for x now. So 100 times 0.10 is 10 minus x equals negative 4. And so now I can add 4 to both sides, or I can subtract 10. It doesn't really matter, but I'll get negative x equals negative 14. Divide both by a negative 1 to get x equals 14. This tile tells me that 14 is the cost of making the cookies. So my total profit will be 100x minus $14 because that's how much it cost me to make the cookies. Now, if I make the cookies for 60 cents each, I can find out the profit by multiplying 100 times 0.6 minus 14, and then we will get 60 minus 14, which will give us $46. So our profit then is $46 if we sell the cookies for 60 cents each. Okay, so again, the key point here is that in this case, we needed to use this other information to find out how much it costs us to make the cookie. And then that's the cost that I'm subtracting from the total amount that I'm going to make when I sell each cookie per a certain amount. Okay, all right. This is an example of a park practice item. So if you have any questions, please feel free to reach out. Please make sure to review your function notation and review what is the input and what is the output, because tomorrow we're going to be looking at that more carefully. All right, the code word for today will be Oreo, since we talked a lot about cookies. All right, happy homeworking and see you tomorrow.